Okay, so this is the last part of section 4.4, the concavity, and the problem is a comprehensive problem that covers the materials from 4.1 to 4.4. So let's take a look. Okay, so it says like this. We have a function x cubed over 3 minus x squared over 2 minus 12x plus 1. And the interval is given is from -5 to 5. So this is our playground. And it asks us a couple of questions. What is the critical point? What is the increase and decreasing intervals? What are the local extreme points, local max or local min? And what is the extreme point? That is the absolute maximum, absolute minimum. And also what is the interval of concavity and the point of inflection. Okay, so that's starting to work on that. So to do that, first step, guys, I would like to take the first derivative and the second derivative of the given function, okay, because we're going to use them a lot. Okay, the first derivative of the function, which is x squared, right, minus x minus 12. Okay. And the second derivative, which gives us is 2x minus 1. Okay. So first step. And step 2, I would like to solve the zeros for the first derivative and the second derivative. Okay, because if you, from this part, we're trying to figure out the critical points. And from the second part, we're trying to figure out the candidate to be a point of inflection. Okay. So for that, x squared minus x minus 12 equals 0. So you got x minus 4, x plus 3 equals 0. So you got x equals -3. F4. Okay. And then this part should be easy. 2x minus 1 equals 0. So you got x equals bar over 2. Okay. Again, so let's take a look at what we found so far. First derivative, second derivative, and those -3 and 4, as you can tell, guys, these are the critical points, right? Because there is no other points gonna make my function, the derivative, first derivative, undefined. So this part is done. And we also find the candidate to be a point to inflection, but we have to verify that. Okay. And okay, so this is what we have. Also, guys, those -3 and 4 are also gonna be the local extreme points, as you can tell. But what are they? Well, we can use the second derivative test for local extreme to do that. Okay, so now let's see. Oops. So this is the second derivative test for a local extreme. Okay, so we can go over them quickly. So in other words, if the second derivative is continuous on an open interval containing C, and here's what it says. Okay, if the first derivative evaluated at C is 0, which is a critical point, as we just see that in -3 and 4. And meanwhile, the second derivative evaluated at this point is positive. In other words, you're gonna have a concave up, right? So in this situation, do you see that you're gonna have a local minimum in this first case? Second case, if f prime evaluated at C is 0, again, critical point, and the second derivative evaluated at this point is less than 0, then it's concave down, right? So you're gonna see that at this point, you're gonna have a local max, okay? And the third situation, if the first derivative evaluated at C and the second derivative evaluate since they are both zeros, we don't have any conclusion. In other words, we have to go back to figure out the increasing decreasing interval on two sides of -3 or 4, and then to make the formal conclusion. So this is about the second derivative test for local extreme. So we're going to use this to handle our problem. Okay. Okay. So let me write. So the first derivative is x squared minus x minus 12. The second derivative is 2x minus 1. The critical point in our problem, which is -3 and 4. Okay. And okay, let's try to see that. And also the candidate point of inflection, which is 1/2, right? Now you set this to 0, solve for that. Okay. So now let's try to see what we have. Okay. Why don't we try to evaluate at -3 and 4 to see whether they are local max or local min? Okay. So use second derivative test. Okay. So f second derivative evaluated -3, it gives us is 2 times -3 minus 1 gives us is -7. So it's less than 0. And then so it's concave down. Hence at x equals -3, I have a local max. Okay. F second derivative evaluated 4, which is 2 times 4 minus 1, gives us a positive 7 greater than 0. So at x equals 4, we have a local minimum because it's concave up. Okay, so a local extreme, we got this part. Okay, so let's flip that to see what we have accomplished. So the local extreme points, this part is down. Okay, this part is down. And let's see, we can also easily to attack this interval of concavity and point of inflection, right? We have a little bit more space here, maybe we can work on that. Now you see that this 1/2, it splits my closed interval -5 to 5 into 2 parts, right? The first one is -5 to 1/2. The other one, which is 1/2 to 5. Okay, so those other intervals here. X sine of, let's see, the second derivative. Okay, because we're trying to figure out the interval of concavity and the point of inflection. So we can take a 0 here, we can take a 1 here, and then we're starting to do the evaluation. Okay, so so let's see, f second derivative evaluated at 0, which is -1, less than 0. Okay, and f second derivative evaluated at 1, which is going to be 1 positive. So we can tell that from -5 to 1/2, which is concave down, right? It's concave down. Sorry about the space. And from 1/2 to 5, it's concave up. So right now you can see that the concavity does change at x equals 1/2. So we can see that, okay, at x equals 1/2, it is a point of inflection. So let's see what we have. The interval of concavity down, point of inflection down. Okay. So the only part left here, guys, is let's see, the increase and decreasing interval and the extreme points. Okay. And so be very, very careful, guys. When we talk about the critical point, we're gonna use the first derivative. Increase and decrease interval, first derivative. Local extreme points, we can use the first derivative or we can use second derivative. Both works, okay? The extreme points, we're gonna use the function itself because we're trying to figure out the absolute max, absolute min. Interval of concavity, second derivative. Point of inflection, second derivative, okay? So we have increase and decreasing interval left, we have extreme points left, okay? So let's use the other side. Okay. So local max, local min, we got that part. So now let's erase this. Okay. So the increase and decreasing interval. So this is -5. This is 5, right? So we have -3. We have 4 here. So you can see that my interval for increasing and decreasing gonna be 3 parts, from -5 to -3, from -3 to 4, and then from 4 to 5, okay? Also want to use a table, okay? X sine of, guys, more space here. Sine of the first group. Okay, so we can pick a point. Let's see -4. Perfect to 0 here, and then we can pick 9/2. Okay, 4.5. And the first derivative is here. And you see, guys, the first derivative function, which is x squared minus x minus 12, it also can be rewritten as x plus 3 times x minus 4, right? I like to rewrite this into the factor form. Why? Because when we're trying to evaluate those values, keep in mind is all we need is to know the sign of its derivative, right? So if we can determine the sign, we don't really need to calculate what is exact value for that. Okay, we only need the sign. So why we write this? Let's try one here. So if we evaluate it at -4, so if I plug into the factor form, I'm gonna be -4 plus 3, right? Times -4 minus -4. So you're gonna have this is, you see, guys, right now we already can get the conclusion because -4 plus 3, this is gonna be a negative sign. -4 minus -4 is also negative. So the product of two negative, it must be a positive. Okay. And f prime evaluated as 0, as you can see, you're gonna have 3 times -4, and again it's a positive sign times a negative, so it's gonna be negative here, and f prime evaluated 9/2, right? So it's 9/2 plus 3 times 9/2 minus 4. As you can see, guys, just to draw 9/3, 9/2 plus 3 is a positive, and 9/2 minus 4 is also positive. So positive multiplied positive here is positive. Okay. And you know, from -5 to -3, and 4 to 5, increasing, -3 to 4, decreasing. Okay. Also, you know, we can also use here to derive. I have an increasing and decreasing, so at x equals -3, you have a local max. You have decreasing, then increase, so that x equals 4, you have local mean. Okay, that agrees well with the conclusion. I erase this part. Okay, so increase and decreasing interval down, and then the last one, we also need to list the table. -5, -3, 4, 5. Okay. So to use this table, guys, you have to evaluate those 4 values to the original function, and then make a comparison to get what is absolute max, what is absolute mean. Okay, so let's see the original function. Fx is x cubed over 3 minus x squared over 2 minus 12x. Couldn't remember the constant. Let's see. Okay, plus 1. Okay, plus 1. So we have to do the dirty work. F -5. So I directly calculate this part, okay, guys, and then you can use calculator to verify. So it's -125 over 3 minus 25 over 2 minus 60 plus 60 and plus 1. Okay, and f of -3, you're gonna have -9 plus 9 over minus 9 over 2 plus 36 plus 1. Okay, f4, which is 64 over 3 minus 8 minus 48, right? And then plus 1, and then f of 5, which is 125 over 3 minus 25 over 2, right, over 2. Let's see. And then minus 60 plus 1. Okay, plus 1. So, you know, we can erase this part. Try to do some basic algebraic operation here. Okay, and let's see. So you have, allow them to have same denominator, 6. So it's 20, 50, 6. So minus 75, right? Plus 360 plus 6. So you're gonna have, what do you have? So I believe you're gonna have 41 over 6. Okay. This one we can do 2 over -18 minus 9 plus 72 plus 2. So you're gonna have let's see. So this is -27 plus 72. You're gonna have 45, and then this is 47 over 2. Okay. This one, you're gonna have what? So we can calculate this part, guys. -56 plus 1, -55. So 64 over 3 minus 165. So you're gonna have -1 over 1 over 3, right? The last one you will have let's see, 6, so it's 250 minus 75 minus 360 plus 6 and let's see, should be good. Okay, should be good. So we have negative, let's see, 256 minus 435 over 6, that's going to give you negative 100 79 over 6. Okay, so I believe that's all the calculations. So a lot of work here, and right now we can find the winner. Okay, the winner. So 41 over 6, 47 over 2, negative 1 over 1 over 3, negative 179 over 6. And here's the winner. So obviously at x equals negative 3, you have the absolute max. Okay? And at negative so at 4, you have the absolute minimum, because this is negative 33 something. This is greater than negative 30, so this is smaller. Okay, so we completed all the problem. Okay, as you can see, guys, I believe overall the procedure is very clear. The only calculation involved part which is when you try to figure out the extreme values, but it's all right. It's just as a practice. Okay, so I'll stop here. Thank you.